Okay, welcome to the 5th class meeting of EECE341, Introduction to Communication Systems. We've just taken the first quiz, and if you have any requests about the technical difficulty we experienced, then please feel free to come to me after the class meeting and ask your request. So as I always emphasize, attendance is not required unless you skip more than or equal to 1/4 of the all class meetings. There will be no penalty until the threshold, but if you cross the line, then I cannot handle that one due to the school regulation. So please check your attendance regularly. And if you have any modification to ask, then please come to me. Handout for chapter 3 is available, so please download it for today's class meeting. And the password is always, as usual, 3 in lower case letters. Quiz 1 will be always, as always, regraded because sometimes our TA and my imagination is below your possible answers. So, however, after the grade is, for example, this Wednesday morning, if you find still your answer, which is correct, is graded incorrect, then please come to me. Homework 5 and 6 will be assigned and due by next Monday. Also, about the previous homeworks, you can always feel free to come to me and ask regrade. I always have emphasized 2 words as an engineer, not just for taking this course. You have to remember these 2 techniques when you want to understand the problem, and also when you want to formulate the problem, and also when you want to solve the problem. Always try to simplify and always try to visualize. Otherwise, you may have a lot of difficulty. Sometimes problems that looks like too difficult to be solved can be very easily handled after you simplify the problem until you can solve the simplified problem. And based on the experience you have to solve the simplified problem, you can solve a little bit generalized one, a little bit more generalized one, and one day or in a moment, you can solve the original problem. Sometimes it comes to your brain that you can further generalize the problem, and sometimes that becomes a good research result. So always try to follow the lessons by Albert Einstein and Claude Shannon. They emphasize the power of simplification. Also, since we have difficulty in thinking abstract, sometimes drawing something is very, very helpful. For example, many of you find yourself that it's very hard to read tables with a lot of numbers. However, if it is just converted to a graph, then we can easily understand. So you feel the power of visualization by simply plotting graphs over a function, right? And sometimes Venn diagram is very, very helpful. Sometimes block diagram is very, very helpful. So try to visualize. In order to visualize, you have to draw or write something. And after you do some other task and come back, that thing, what you have drawn or written, helps you. So it's like you copy yourself and put yourself aside you and ask him or her to help me. So by writing down, visualizing, you can multiply your power of brain. So never forget these two messages from me. So this is, I always tell the undergraduate students. So think about year 2036, okay? So around 10 years later from, 12 years later from today. And you have, in the meantime, you have graduated, you have got higher degree like master's or PhD, and you had some experience. And for example, you started a venture and you've become a very famous man. You gained a lot and remembered the experience at Posttech. So you decided to donate a lot of money to the university. And today is the day you come to the campus and meet the president of the university and shake hands and have some ceremony, and you donate the scholarship fund, something like that. And you walk around the campus and you meet me, who is going to retire because of the age limit. And I suddenly grab your neck and ask, what is my lesson to you? And if you murmur, then I will kick your ankle, okay? Kick your knee. But if you say that, simplify and visualize, and then I will let you go, okay? So please remember these two words. It will change your life. I bet you. Okay. I have received some questions about what is the meaning of a negative frequency. So I've seen actually this one from some famous popular science book. And the author, when he was very young, have seen some magazine that has the cover page saying that by using negative frequency, we can generate black light. So if you emit that black light, the spot is invisible, something like that. And since he had no idea as a kid about the negative frequency, he believed. And now I'm asking you, what is a negative frequency? Actually, when we were high schoolers, what was the definition of period of a periodic signal? And what is the definition of frequency of a periodic signal? So be careful. In our high school maths or physics, the definition of periodic signal was simple. Something goes over again and again with the same time interval. So let's say period is positive as we defined. Then what was the definition of frequency? Definition of frequency was the inverse of the period, right? And now, since t is positive, frequency cannot be negative. That may be one of your misconceptions about frequency. Of course, your misconception is half correct. According to your high school definition, there is no negative frequency. Consider that. Suppose I draw sine functions and cosine functions. Which one has negative frequency? So let me draw. Okay. Which one has negative frequency? According to our ordinary high school definition, there is no negative frequency. But we say in signal gen systems and afterwards talk a lot about negative frequency. What's going on? So the answer is very simple. Negative frequency is defined, okay, in Fourier analysis. Got it? Negative frequency is defined in Fourier analysis as what? Because in Fourier analysis, what is important is so-called the complex sinusoidal signal. And in complex sinusoidal signal, if this F is negative, no problem, right? It's just a signal. So in complex sinusoidal signal, if this one is negative, then we just say that it has negative frequency. Got it? So the story is like this. Whenever we want to introduce new concept, we reuse the word that has been already defined. So as in computer science, it's like you redefine a variable. So you define a variable temp to be used as an integer, and after several lines, you redefine that one in Python or MATLAB as a Boolean variable, something like that. You can do that. Similarly, what we do in this academia is that we take some words already available because we cannot name new concept using totally different one because we are learning out of the words. Got it? So it's like you have a word. You have a definition of a word. Sometimes it is redefined to become more general. Sometimes it is redefined to be more specific. Never forget this as an engineering student because many words you use may have different meanings. For example, even in electrical engineering, sometimes we use the term channel. For communications theory engineer, this channel is understood as something between transmitter and receiver. Everything between transmitter and receiver is a channel. However, so this is my point of view. However, for some signal processing people, suppose you have some data acquisition board. Then what does that mean by channel? Channel means the input and output terminal. They call this as channel. So if the data acquisition board has 5 input terminals, node or something, they say that it's 5-channel data acquisition board. Do you understand what I mean? So even in this same electrical engineering building, we use the same word as for totally different meaning. Got it? So now let's go back to the negative frequency. If you still stick to the high school definition, negative frequency cannot be understood. However, if you remember that, you now have redefined the concept of frequency, and especially if you focus on complex sinusoidal signal, negative frequency means a lot because see that e to the j 2 pi t and e to the negative j 2 pi t are different signals with the same period, right? The first one can be written as cosine 2 pi t plus j sine 2 pi t, but the second one is cosine 2 pi t minus j sine 2 pi t. So they are different signals. Got it? So don't be frustrated by the notion of negative frequency. Just revise your dictionary. So delete that part of your dictionary with old definition and rewrite it. Okay, here goes the big picture or course outline, and we are now here. And even though we covered the first 2 chapters very quickly, this chapter 3 may take a month. I don't know. Even I do not guarantee. I hope I want to finish it by within 4 class meetings. But anyway, today is already half gone. So probably after chapter 3, we take the midterm exam. I want to emphasize that chapter 3 is the most important chapter in this course, got it? And it requires the knowledge on signal-gen systems, especially Fourier transform. That's why we have taken our first quiz covering signal-gen systems, got it? Okay. Here goes the preview of today's class meeting. It's kind of review, but be careful. So here I have drawn a Venn diagram, even though people who have better definition say that this is an Euler's diagram, not Venn diagram. But anyway, you know what I mean. So this is the set of all communication. So this may have some communication technology stand to phone. You know that, right? What you know who is Stento, right? By the way, during the Chuseok break, I've watched the Hercules played by the famous actor, and of course there was no Stento appearing, even though he was a very important hero in Iliad to communication engineers. But anyway, so here goes a signal fire and smoke, or signal flag technology. And I don't know how to Pabar system, those things. All important, but not our interest. Here is a very small subset, even though a lot exaggerated. And this subset is called the electrical communications. It includes all communication technologies using electrical systems. Got it? So there flows some current. There moves some electrons and holes. Okay? And among electrical communications, there is another subset called radio communications. What's the difference between electrical communications and radio communications? Radio communications use radio wave, which is the lower part of the electromagnetic wave. So, for example, suppose we use infrared to control our camera. This is transmitter and there is a receiver. This is not radio. Got it? Sometimes the term radio is used to mean a system that utilize radio wave to do something. Got it? So this is not a radio. Got it? And this is a radio when I use it to access to Wi-Fi system or a cellular system. So the focus of chapter 3 is what? Among electrical communications, we focus on radio communication. Got it? So we narrow down our interest, as we've done in signal-gen systems. First, we talked about every possible signal-gen systems, and we narrow down to our interest to what? Linear time invariant systems. Be careful. Many of you cannot well distinguish linear systems and linear time invariant systems. Because in signal-gen systems, we too much talked about linear time invariant systems. However, linear system, which may be time varying, is very, very important, especially in communications. However, we will rarely talk about it, and we wait until you take some courses in control systems, automatic control. Then you will see impulse response, for example, for a general linear system, not linear time invariant system. And some of you already know because when I taught signals and systems, I have shown the form of impulse response for general linear time varying systems, which has two parameters. So it's like output of a linear system is what? Not ordinary convolution, but this strange integration. And I say that this h of t tau is the impulse response of the linear system at time t to the impulse that is applied at time tau. And if this two variable impulse response has some interesting property called time invariance, then we have what? The famous convolution integral. Got it? So this is for general linear system. And this is specific for linear time invariant system. Anyway, we are going to focus on radio communications in this chapter. Got it? This is the most important part of chapter 3. We are interested in communications, especially electrical communications, especially radio communication. Got it? Now, in radio communications, what is the most important component of the system? Of course, depending on different point of view, the answer will vary. But I myself believe what is most important, the most important device or component, physical component in radio communications is an antenna. What is an antenna? Antenna is an interesting thing that converts wave into electrical current or voltage. Got it? So just think about your cell phone, smartphone. It has microphone. It has a speaker. What's the function of the microphone and speaker? Microphone converts acoustic signal into electrical signal. What is the function of speaker? It converts electrical signal, current or voltage, to acoustic signal. Very similar thing happens when you use antenna in your radio. Antenna, if an electrical signal is applied, it generates radio wave. And also, if radio wave impinges on this antenna, suppose this is antenna, then you can extract some current or voltage at the terminal. That is antenna. So the antenna may be transmit antenna or receive antenna, and microphone and speaker has very good analogy. Got it? Now, some of you may say that, okay, if we talk about radio wave, do we have to use Maxwell's 4 equations to do some electrical communications? Sometimes the answer is yes, but interestingly, in many cases, the answer is no. Why? Because in many parts of the radio communications, we only consider after the radio wave is converted to electrical signal. So here, there will be a lot of buildings and some environment for radio wave to propagate. So you have electric field that is a vector field with 2 arguments, location vector x and time t, and also electric or magnetic field that is also the function of x and t. And we have that curls and divergences, those things. However, once the antenna converts this wave that affects the electrons and other things in the antenna and gives the motion of electron. What is this? You have possibly RF cable, and eventually you can model this one using a time function. So even though radio wave is a wave, we do not handle it as a wave. We just handle it as a time function. Got it? That's why signals and systems, not electromagnetic theory, is important in this course. Got it? So we mainly talk about the signal that is to be applied to the transmit antenna, and the signal that is extracted from the receive antenna. Of course, this point of view has a lot of limitation. However, it is one of the most important way to understand radio communication. Got it? So let's say hooray, because I'm not going to write down Maxwell's equations in this course. So if you really hated that one, you can still become a radio engineer. Now, let's classify these two signals. Of course, these are models. Got it? These are mathematical models of something at the input to the transmit antenna and something at the output from the receive antenna. We model the current or voltage as a continuous time signal. First question, is it real valued or complex valued? Because any function, mathematically speaking, requires domain that would be R, because there is no imaginary time, and codomain. What would be the best choice? If we think about voltage or current, there is no complex voltage or current. And you may say that, wait a minute, I've learned a lot about complex signals in circuit theory. As I emphasized, that is what? That is a representation of real band passing. As I told you already, suppose you have some A cosine, I hate omega, but omega 0 t plus theta, that in some alternating current circuit, AC circuit, instead of using this one, what did you use? You use this phasor, right? And you may say that, hey, I have a complex signal. But actually, you don't have a complex signal. You have a real signal that is represented by complex scalar. So here, what is the most important is that our model of the input to the antenna is a real valued time function. Got it? So this part is very important. Similarly, here, y is also real value. Now, let's think about, imagine you are an assistant to Guglielmo Marconi in 1890 something, okay? So you want to use radio wave to transmit telegraph signal. What do? You build some electrical system. And as I told you, because you've taken your time machine to become assistant to Marconi, you know that you need an antenna. What kind of antenna Marconi initially used? As I told you, Marconi get a good education, but not this public education. Actually, he was intensively taught by his parents, especially mother, and some other private teachers. Probably he didn't have understanding about Maxwell's equations. The best thing is that you already know Heinrich Hertz successfully demonstrated the existence of radio wave or electromagnetic wave by using what? Spark gap, right? So he also adopted that one. So by using spark gap, he wanted to transmit telegraph signal, 200 meters, 600 meters, 2 kilometers. What is the problem? So if you remember from some of figures, there is a metallic balls with very small gap, and it has some, the electrical system has some coils and capacitors, and of course, resistors. What would happen? They charge the capacitor to store the energy in the space and release it. What happens? You have so-called damped oscillation. So this spark gap, actually, one of the first observers have seen that this spark, some right? And they've seen something really oscillates. So using this spark gap transmitter, they couldn't generate so-called sinusoidal signal. They could only generate what? Some signal like this. And then they recharge, and then again, some short pulse with damped oscillation. Now, what do you do to transmit telegraph signal? By using the key, you may switch on and off this thing. For example, you push it, then you have that one. So you put a window, then B, right? And then you put here B and 0. Got it? By using the key and by doing keying, you can transmit dot and dash. By the way, probably you've never used the key for telegraph. And our city, Pohang City, has a National Museum of Lighthouse at Komigot. And probably many of you never know the fact. And it has 2 places where you can use the telegraph key to not send, but to test your message. If you want, why don't we go to all together, go to the National Museum of Lighthouse and have some competition about using the telegraph key. But anyway, I have, it seems, around 1 minute, less than 1 minute. And let me emphasize. So in the beginning of the radio communication, there was no sinusoidal signal that may last for 2 seconds or 3 seconds. Very short pulses with damped oscillation could be generated and generated and generated by doing switching, charging, and charging the capacitor or inductor and generate some damped oscillation and recharge, generate. And by doing that, you could send a telegraph message. So continuous wave, we are going to talk about in this chapter 3 handout, was an amazing breakthrough, so-called disruptive technology at the time, in the early stage of radio communication. And we assume that this continuous wave, for example, cosine 2 pi some f0 t plus theta, some signal exists, but this is not easy. That's why one of your electronics circuits lab asks you to generate sinusoidal signal by doing some feedback to your transistor. Anyway, this is all for today's class meeting, and we will continue on this Wednesday. Okay, that's all for today.